So if I were you and I were taking notes, just to review what we learned in the last section, I would go to this spot in my packet, and for on the circle, I would write angle equals arc divided by 2. And for this one, do you remember? There's actually two arcs involved. Arc plus arc divided by 2. And for the vertex outside the circle, again, two arcs involved. Arc minus arc divided by 2. So, yeah, I thought it was nice just to have all those formulas in one place. The last thing in this section is about polygons in a circle. So if you have just this nice little triangle nestled so snugly in that circle, we call that an inscribed triangle. And this would be an inscribed quadrilateral. Look how snug it is. And the circle that goes around it is the circumscribed circle. So I wanted to just kind of play around with what kinds of four-sided shapes I could fit into my circles here. Could I fit a square into a circle? I think I could. I didn't draw that very well, but it's the thought that counts. How about a trapezoid? Could I draw a trapezoid? It's pretty good. Kind of feels isosceles to me. So anyway, there's some theorems that are related to shapes that are inscribed in a circle. And the first one is about a special type of triangle. It's the right triangle. And the right triangle, the right angle being right here for this picture. Well, funny thing, if you kind of look at how that right angle opens up, did you see that the arc that it's intercepting over here winds up being half the circle? And that actually is the only way you could fit a right triangle snugly into a circle, is if that was a semicircle over there. So if that's 180 degrees, that's going to be 90 degrees, and that fits with our little theorem that we learned yesterday. And so for a right triangle, the theorem goes that if you have a right triangle inscribed in here, then the radius, nope, I said that wrong, then the diameter of the circle has to be the hypotenuse of the right triangle. Does that kind of make sense? That's just the only way that a right triangle will fit in there. And for quadrilaterals, this is kind of a crazy theorem. So actually not every four-sided shape will fit into a circle. Let's think about trying to draw a parallelogram in one of these. A parallelogram. So as soon as I get two sides to fit nicely in another side, as soon as I try to get this, do you see how that corner doesn't quite make it? It's really hard to get just your regular, that actually looks more like a rhombus, but to get a parallelogram to fit in there, it's not going to work. And there's a theorem that says that there's a relationship between opposite angles that fit inside a circle. If you have an inscribed quadrilateral, those two angles actually have to add up to 180. The opposite angles are supplementary. And I can explain why that happens, but just for funsies, let's figure out how big y is first. We know that the y plus the 68 has to equal 180. So y would be, is that 112 degrees? Now the reason this works is, so let's focus on that 68 degree angle. Do you see that alligator mouth? So this arc right here would have to be 68 times 2, is that 136? Okay, and then if we focus on the other angle, the angle y, we just figured out that that was 112 degrees. And you see this red alligator is chomping on this arc. And so 112 times 2 is 224. And what does 224 plus 136 equal? It equals 360 because we just used up the entire circle. And so since the arcs add up to 360, the angles add up to 180. That's the reason this theorem works. I just think that's neat. How are we going to find x? We know that the x and the 82 are supplementary. So x would have to be a 98-degree angle. And if you add up the 4 angles in a quadrilateral, we should get 360 and minus 2 times 180. So those are some fun theorems about shapes inside of our circle.